In last week's lectures, we learned about several applications of Monte Carlo methods to estimation. This includes the estimation of the expectation or the mean of a statistic. When your statistic is an unbiased estimator of your parameter of interest, then we know that the expectation that we can estimate is just the parameter of interest. We also learned how we can use Monte Carlo methods to conduct simulation studies to study the mean squared error of an estimator. In addition, we learned how we can approximate the confidence level of a confidence interval using Monte Carlo methods. This week, we will spend our time talking about another application of Monte Carlo methods to statistical inference, and this is for hypothesis testing. I hope you remember something about hypothesis testing from your previous statistics courses. This is one of the most commonly used things in statistics. So suppose we are interested in a parameter theta that describes our distribution x. Theta can be any parameter that characterizes some properties of our distribution x. This time, instead of getting a point estimate of theta, we want to instead perform a hypothesis test about theta. Our null hypothesis, H0, is that theta belongs to the subset theta 0. So the really chubby theta here is capital theta. So this is a subset. And we have an alternative hypothesis. And that's when theta belongs to another set, theta 1. So here, theta 0 and theta 1 are disjoint partitions or subsets of the parameter space of theta. And we denote the entire parameter space of theta by this large theta. And this is the set of possible values that theta can take. So essentially, we want to use the observed data to find out, is theta belonging to the set theta 0, or is it more likely that theta belongs to the set theta 1? So here are a few examples that you might be familiar with. The first is the z-test, which is probably the first statistical hypothesis test you have learned. So in the z-test, we are interested in testing a hypothesis about the population mean. Suppose we know the population standard deviation or the population variance, and we want to know whether the mean of our population is equal to some mu0 or not. Then we can perform the two-sided z-test, where the null hypothesis is theta equals mu0, and the alternative hypothesis H1 is theta is not equal to mu0. In other words, the complement of theta equals mu0. Another one is the t-test, where we are still testing the null hypothesis of whether our mean is equal to mu0. However, in this case, the population variance is unknown, and we have to estimate that from the data as well. Another example you might be familiar with if you have taken courses on regression or modeling is the Wald test. So the Wald test is useful for testing hypotheses about model or regression parameters. For example, you fitted a regression and you're interested in whether the slope in front of a dependent variable should be equal to 0 or not. If it's equal to 0, it means that this dependent variable probably does not contribute to the prediction of your, the slope in front of the independent variable, your predictors. So if it's equal to 0, it means that this predictor probably isn't very useful in the prediction of our dependent variable y. So for the Wald test, the null hypothesis is that your coefficient in the model, it can be a slope or an intercept, is equal to some fixed value beta 0. And the alternative is it can be beta is not equal to beta 0. So based on a random sample of X, we will decide whether we want to reject or retain. Retain meaning we want to accept or not reject the null hypothesis H0. How is this done? Well, we need to start by defining a test statistic. Let's suppose x1, x2, all the way up to xn is a random sample from the distribution X. Performing hypothesis testing would require us to first specify a test statistic, t, that is equal to a function of your random samples. So t is equal to a function t applied to x1, x2, all the way up to xn. So you can see that t is a statistic. And because we're using it for performing hypothesis tests, we call it a test statistic. Some examples you might be familiar with are the following. For the z-test, the test statistic is the sample mean x bar minus mu0 divided by the population mean divided by the square root of your sample size n. Here, you can see that this is a function of your random samples because x bar is a function of your random samples. It's a sum of all of them divided by n. The rest of them are known under the null hypothesis, so they're just constants. Another one is the t-test. In this case, everything else is quite similar except we replace the known population standard deviation by an estimate of it, which is a sample estimate of the standard deviation. For the Wald test, the test statistic is given by beta hat, which is your point estimate for the beta parameter, minus beta 0, which is your null beta value, divided by the standard error of your beta hat. From this point, once you have the null and alternative hypotheses and you have the test statistic, you can find the sampling distribution of t. In other words, the function t applied to your x1 all the way up to xn. Sorry, it should be x here. Under the null hypothesis. So the sampling distribution of t under the null hypothesis is sometimes also called the null distribution of your test statistic. Then, using the null distribution of t, we can find a rejection region, that is, an interval C, such that the probability that t belongs to this interval C under the null hypothesis is equal to alpha. Here, alpha is a pre-specified type 1 error rate that we'd like to control. We'll talk more about this on the next slides. And then, once you have your test statistic and you have the rejection region, that is the region in which you will reject the null hypothesis, given some observed data that we collected some samples and observed some values, x1 all the way up to xn. We can plug this into the formula for t, compute the t, and if this t is inside this rejection region, so if t applied to x1 all the way up to xn is inside C, then we reject the null hypothesis. Otherwise, so if t is not in this rejection region, we retain the null hypothesis. So here's a concrete example. For the z-test, under the null hypothesis that the mean is actually equal to mu0, our test statistic x bar minus mu0 divided by sigma divided by square root of n follows the standard normal distribution. If we want our alpha, which is the type 1 error rate, to be 0.05, then the rejection region will be given by C equals the interval from negative infinity to negative 1.96, union the interval between 1.96 and positive infinity. So in this case, the cutoffs of positive or negative 1.96 are also called the critical values. So if this statistic that you compute from the sample lies in this region, so if it's below negative 1.96 or above 1.96, then you reject the null hypothesis and decide that based on the observed data, we reject the null hypothesis that the mean of our samples is equal to mu0. Otherwise, if it's between negative 1.96 and 1.96, then we do not reject the null hypothesis. So that was just a brief review of hypothesis testing. For hypothesis testing, we can always construct a 2x2 table, where one margin is the ground truth. So in reality, is H0 true or false? The other margin, so our columns over here, is the decision we make based on our test statistic. Based on the test statistic, we might decide whether we want to accept the null hypothesis or do we reject the null hypothesis. So given the ground truth and the decision we make, there are 4 types of possible outcomes. 2 of them are correct decisions. This is the case where the null hypothesis is true and we indeed accept the null hypothesis. The other case, which is at the bottom right, is the case where the null hypothesis is false. In other words, the alternative hypothesis is H1 is true, and we indeed reject the null hypothesis. However, the other 2 outcomes are errors that we can make. The 2 types of errors we can make include the type 1 error. This is the case where we reject the null hypothesis when the null hypothesis is actually true. And the second type is type 2 error. This is the case where we do not reject the null hypothesis when the null hypothesis is actually false. So we denote the type 1 error here by alpha and the type 2 error here by beta. And this alpha is the same alpha as the one that we try to used to find the rejection region on the last slide. So when you're trying to make the decision, there's always a trade-off between type 2 and type 1 error. It's impossible for you to minimize both at the same time. So if you're extremely cautious and say, I don't want to make any type 2 error, then in that case, you might just reject the null hypothesis all the time. Then your type 1 error will be really high because you will have a lot of false positives. On the other hand, if you say, I always accept the null hypothesis, then your type 1 error will be really low. So alpha is going to be equal to 0. However, you will be having very high type 2 error. So in that case, whenever the H1 is actually true, you still decide to accept H0 and you're making the other type of error. So you see there's a trade-off between these 2 and we cannot minimize them both at the same time. What we usually do in statistics is to try to control the type 1 error rate under a threshold alpha. So this is why earlier we would try to find the critical region or the rejection region by pre-specifying a level of alpha we would like to achieve. So in this case, we want to control our type 1 error rate, which is rejecting the null when the null is actually true, under, say, 0.05. And then with this restriction, we try to find the most powerful test. In other words, the test with the lowest beta, the lowest type 2 error rate that satisfies this. You should also note that the power of a test is given by 1 minus beta, which is 1 minus the type 2 error rate. So what we're trying to do is finding a hypothesis test, a test statistic, and a region that um, controls our alpha, so it achieves a type 1 error rate, say less than 0.05. And then under this restriction, we try to find which test can achieve the highest power or the lowest type 2 error rate. So you might ask, when does Monte Carlo methods come into play over here? It doesn't seem to involve Monte Carlo methods. Well, the answer is still related to the distribution of our statistic, in this case, the test statistic. It turns out the null distribution of t, our test statistic, is not always easy to find. For example, if you're trying to do the t-test, and you know that your xi's are normally distributed, then we can be pretty sure that our t, which is the test statistic defined this way, is distributed under the null hypothesis according to the t distribution. However, we don't know what will happen if the normality is not satisfied. So in this case, it's not exactly going to follow the t distribution. And we might still be interested in what is going to be the null distribution of t when the normality doesn't hold. Another example is when your test statistic looks unconventional. So there are many test statistics that you might be familiar with, such as the one that looks like this. However, you can, because t is a function of your data, this function technically can be anything. So your test statistic can be any function of your observed data. For example, it can be the trim mean, which we discussed in week 5, or it can be something that's even more complex. So for example, I'm just giving a really weird example here. So your test statistic is the area under the logistic curve that is fitted with data x1 all the way up to xn. In these cases, we can again use Monte Carlo methods to approximate the null distribution of the test statistic. And this will be useful for analyzing both the type 1 error rate of our hypothesis testing procedure, as well as the power of a hypothesis test.